Human tissues are comprised of incredibly intricate, three-dimensional biological entities, from benign cells and structures for a healthy person to cancerous cells, glands, and tumor microenvironment for a cancer patient. For over 100 years, pathologists have been diagnosing cancers and diseases by examining thin, two-dimensional tissue slices cut from an excised tissue specimen during biopsy. However, such thin, 2D slices provide only a glimpse of the tissue's true complexity, as the excised tissue specimen is volumetric and heterogeneous. This is why there is a growing push towards looking at tissues in their natural 3D form and eventually ushering in a new 3D pathology paradigm. We need two innovations in tandem to make the leap into 3D pathology. First, the hardware. Advanced imaging equipment and protocols that can capture the detailed 3D structure of tissue specimens. Second, the software. Manual examination by pathologists of the 3D pathology dataset, which can contain 100 times more slices along the new depth dimension, is going to be practically infeasible. Therefore, we need a sophisticated pipeline that can distill these complex and massive 3D structures into patient-level clinical insights, creating computer systems capable of efficiently and accurately making sense of the enormous amount of image data remains challenging. Our work, TriPath, focuses on bridging such computational gaps. TriPath is a deep learning platform for processing tissue volumes and predicting clinical outcomes based on 3D morphological features. It is comprised of two steps: data pre-processing and computational processing. First, the raw volumetric 3D pathology image is divided into a set of smaller 3D patches to facilitate computational processing on the enormous input. Next, a representative and low-dimensional feature is extracted for each 3D patch, and these 3D patch features are aggregated together to form the volume-level representation, which yields the patient outcome prediction. In this study, recurrence risk stratification models were trained on prostate cancer specimens at Mass General Brigham and the University of Washington, imaged with microcomputed tomography and open-top light sheet microscopy. By comprehensively capturing 3D morphologies from the entire tissue volume, our approach achieves superior performance to the clinical report baseline and 2D deep learning models applied on a few slices, or all slices, from the tissue volume. For clinical validation, 6 board-certified pathologists with a mean clinical experience of 26.5 years provided diagnosis on select slices from the same sample that TriPath examined. TriPath was still able to outperform the clinical baselines from the pathologists. Further interpretability analysis confirms that TriPath identifies the high-risk morphology in agreement with the current clinical literature. The high-risk morphology corresponds to Gleason pattern 4 and 5, whereas the low-risk morphology corresponds to benign glands that are non-cancerous. Here are some additional examples of such heat maps. With the rapid growth and adoption of 3D spatial biology techniques, TriPath provides a general and efficient computational framework for clinical decision support and can help to reveal novel 3D morphological biomarkers for prognosis and therapeutic response.